Good morning. Thank you so much for coming. This is the first of our Epic Game Tech Talks for the day. This one is called Causing Chaos, the Future of Physics and Destruction in Unreal Engine 4. I'm Matthias Worch. I'm the design lead at the Special Projects Group at Epic, and I'm here to tell you about designing with chaos. We have three other speakers. I'm going to be followed by Jim Van Allen. He's a senior technical artist. He's going to talk about the art of destruction. Then we have Michael Lentine, lead physics programmer, and he's going to illuminate the tech behind chaos. And then we're going to close it out with Jeff Roos from Intel. He's going to tell you a little bit about what we did to make chaos fast. Now, we just unveiled chaos to the world at the State of Unreal keynote that we just saw. To give you, in case you didn't see it, just some quick overview. Chaos is Unreal Engine's new upcoming physics system. It's in active development right now. We're working on it. We're going to release a preview version of this with 4.23, so you can get ready. And it's a complete physics system. It's going to do everything you expect a physics system to do brilliantly. It also happens to be incredibly good at destruction. So when we were thinking about how we should reveal this system to the world, we figured we should make a little arcade game, a little shooter that allows you to smash stuff up. And we just showed this live here on stage during the keynote. Don't worry, if you didn't see this keynote, there's going to be a lot of video coming up. Right now you can already see some from the screenshots here. Everything you saw here was happening in the engine and live. So I'm going to tell you a little bit about it, and then you're going to see a whole bunch of video that actually shows all of this in action as well. So the actual design brief behind this demo was pretty simple, right? We wanted to create an homage to the old light gun games that allows you to smash stuff up, allows you to achieve a goal. You're chasing after this little robot. She's called KOS, or Chaos. You're trying to hunt her down. And as you're doing it, you are using destruction as a tool. Now, everything that you see in these shots, everything that you will be able to play at our booth, by the way, I very much encourage you to stop by. We have 2 big stations where you can play this. I've played this over 200 times now, and I still can't get enough of it. Everything you're able to do there was completely created in the Unreal Engine. Everything was done in Unreal Ed. So the only thing you need to do to create something similarly amazing is to download Unreal Engine 4 for free, and you're off to the races. And the reason why I love that everything actually is in the editor is because it shows you how fully integrated Chaos is with the rest of the engine. Chaos can talk to all the other systems can talk to Chaos. And that's incredibly important when we want to make something like destruction gameplay relevant. So we're going to come back to that in a bit. Everything you see in these shots that you can play at the booth as well is running in real time as well. So we're rendering this on a regular high-end gaming PC. You could go to the store and buy it right now. This is not something that is way off into the future. Everything we're talking about here is attainable right now. And there are a whole bunch of scalability options as well that allow us to run this kind of system at lower level platforms. You're going to hear about more of this from Michael Lentine later. Now, there is a difference between rendering something at runtime and in real time. We've done that quite a bit. And simulating something at real time, right? Because a physics-heavy system like this destruction system that we have here needs to actually do all of those computations. So if we dig into this, I just want to assure you that everything that you can see, that you can play, that you saw in the keynote, is simulating in real time as well. With one caveat, of course. Everything is simulating at real time whenever we need it to. And this is a really interesting distinction, so I want to dig into this a little bit, because if you understand this, you really understand what makes chaos so truly powerful and amazing. So we have 3 sections in this demo. We have this first initial section where you're hunting chaos through a street city scene, and you're trying to hunt her down, you're smashing up the environment. Everything you see right here, 100% rendered and simulating at runtime, which I'm sure you can see the reason for immediately, right? We have no idea where you're going to shoot, so we need to make sure this is a fully destructible environment, and you can take all of this down. Then we have a second section where Chaos is trying to hide in a couple of buildings. She's trying to get away from us, and we are flushing her out by just laying waste to the entire building. And once again, both of these buildings, everything that you see here, 100% rendering and simulating in real time, including robo-ready headquarters. Now then we get to this third sequence. And here we're doing things a little bit differently, because this is a cutscene, and we're actually flattening an entire city block right here. So what we actually did here is pre-simulate every single piece of destruction for every single building right here. We saved that, we cached it, and now we're playing it back at real time. Now, this might make it sound like there's a clear distinction between sequence 1 and sequence 2, where we're actually smashing stuff up ourselves and what's happening in this cutscene. But if you're actually looking under the hood, that's not the case at all. Chaos can pre-bake simulations and play them back at runtime. And that's actually really good for us, because it allows us to art direct these kind of demolition moments, right? We can control the pacing perfectly. We actually had this third sequence hooked up in Sequencer, so we could hook up the effects exactly and the sound effects exactly where we wanted it to. And then it does allow us to create something that runs at perf for sequences, just set pieces, which are as big as this. Because this is an entire city block. It's luckily unoccupied, by the way. It's a construction zone. But these are 5 skyscrapers, which are all coming down. I don't even know the number of rigid bodies that we have in this sequence. This is how we can actually have this run and have everything never leave gameplay, never actually play a movie. Now, what's really cool about Chaos is that under the hood, the way that sequence 1 and 2 and 3 were authored, there really isn't a difference. We used exactly the same tools. We fractured things exactly the same way. We're using this new asset type called a geometry collection. This is pretty much whenever you want to smash something up in Unreal, you use a geometry collection. You're going to hear more about it. But a geometry collection doesn't really care how it gets smashed up and how it simulates. It doesn't really care if something is pre-baked or just simulating at runtime. What's really cool about Chaos is that any part, even of a pre-baked simulation, can become active at any time. It means that destruction in Chaos, even when something is pre-simulated, is never static. If you input a stimulus into that system, like let's say the player is shooting at something, for example, Chaos can react to that. That specific part of the simulation actually becomes active. So Chaos can react to the dynamic world state. You don't have to worry about sanitizing your scene ahead of time. It actually can react to every single piece of runtime simulation that you created before you started playing this demolition event. And this keeps everything incredibly performant, even in this third vignette, right? Because we pre-baked out 5 large skyscrapers collapsing on you. But because only the parts that we're interacting with actually become active, we're adding a tiny bit of overhead, but everything still stays really, really performant. And this is how we could dream big. This is how we could create this situation. And this is how we could go back to Robo-Ready headquarters, for example. We could turn this into an awesome art-directed destruction piece instead, where we're setting up the charges exactly the right way. And then this might become a great set piece in our game. But what we can do with Chaos is actually take the player, and if we want to put her right at the bottom of this building, and want her to be in the sphere of influence of this destruction event, we could do that. If we want to create gameplay where we create something where the player has to spray bullets because there's all of these pieces of debris falling down on her, and the only way she can survive is to make sure she breaks up all of that rubble that's coming at her, we can actually do that. Because the pieces of debris, no matter where she's standing, that are raining down on her, those are going to become active, and those are going to allow her to survive. And this is literally a game changer, right? Like, we could not do this before. The player with Chaos can always be an active participant. We don't have to wall things off anymore or put the player in a bubble because we were really worried that she was going to find out how our static playback that we were just playing back from another program is just that. It's complete trickery. Everything in Chaos is actually running at runtime. And Chaos can do this because it's a system. It's a physics system. It's a first-class citizen of Unreal Engine 4. It lives alongside all of the other runtime systems which you already have simulating your world, which are already running your game. So Chaos can be triggered, Chaos can be queried, and Chaos can send events. And that creates some incredibly tight integration with all of the other gameplay systems. Now, this was incredibly important to us. We wanted to make sure that this was possible from the beginning, because this is how we as designers and as gameplay engineers actually knew that we could create actual gameplay around a system like this. Because let's be honest, this is awesome, but it's also a little bit scary, right? Like, if I was sitting in the audience right now, I think my first reaction as a designer would be that demolition is awesome, but it's an inherently messy system. And what's so funny about messy systems is that they're unpredictable. They rarely play out the same way. They probably actually never play out the same way if they're a true system. And once we add a player to that situation, and we don't know where she's going to shoot, where she's going to put the camera, etc., we add a whole bunch of uncertainty. And ultimately, this is cool. This is why we're doing this. This is why we love physics system and destruction as a toy, right? This is how we can use destruction as a tool to create increasingly more expressive gameplay experiences. We can add that whole level of expression on top of it. But we want to make sure that we can actually manage all of this. So we wanted to make sure that we did all of this extra work very early on to make sure we can account for all of this chaos that we're literally creating. And we do this, of course, by creating runtime systems and behaviors that are actually aware of this demolition, that can interact with it, and that can overcome anything that we might quite literally throw in its way, right? We might even be able to create systems this way that take advantage of this kind of demolition. So I want to give you some examples. This is an incredibly broad topic. I could talk about this for hours probably, and we're just scratching the surface. But I want to give you some examples from the actual demo that you saw footage of here to give you an idea of how we created this and how you should get ready. And because I'm a game designer, the very first slide I'm going to show you is incredibly ugly because I took it from the editor. So you're warned, there's a sea of green here, but this is a kill field. And the reason I like showing this first is because it's a good example of how, if you don't want to change anything else about your game, you can very selectively sanitize your scenes. Let's imagine you want to have this awesome destruction set piece that is playing right over here, and afterwards you know that there is going to be a really good encounter that somebody put a lot of work into over here. And you're worried about the demolition influencing that encounter in some shape or form. Well, because in chaos, nothing is ever static, you can very selectively put a kill field right where that encounter is going to play out, and you can only destroy the rubble which was created in that specific part of the level, and you can get rid of it. You can actually reduce it to smaller pieces of rubble, so it still looks integrated with the large-scale destruction you just saw, which you can still see all around you, but that specific part of the level has now been sanitized, and nothing has changed. Now, I'm hoping, of course, that you're going to try to use demolition in gameplay-relevant context, right? And this is where I want to go a little bit deeper into the fundamental systems, or some of the fundamental systems that you're going to be interested in. Let's start with navigation, because that is pretty much the absolute baseline of how an AI is actually going to interact with this. And this is very simple. Nav is fully supported. We already made sure that nav mesh works on geometry collections. You can also create dynamic nav mesh if you want to, and you could actually have that be modified by the debris that you're generating. So in this shot that you see right here, I see it's even more green, I apologize. You have 3 nav mesh islands, and 2 of them are on geometry collections, and 1 of them is actually on a static mesh. And so if you were to shoot this bridge right here, you could cut into the nav mesh. The guy standing on that bridge could fall down, probably to his death. And all of the debris, which is going to rain down on the nav mesh below, can actually modify that nav. And then your AI can actually react to that and make decisions accordingly. Now, it turns out we didn't actually have to do this for this demo. We realized that we could do something simpler, which we lovingly called a cow catcher or snowplow, because we realized that for the kind of playable area that we have in this demo, the kinds of debris we had was never so big that you would expect somebody to be fully blocked by it. We realized that if we just have AI collide with it and kick it down the road, so to speak, that was actually working. So all the debris that's falling on the ground in the chaos demo goes to sleep once it hits the ground, because that's how we keep things performant. But again, it never becomes static. It's never completely taken out of the simulation. So as soon as one of our AI is running into debris, he can actually kick that along, and that actually looked good enough for us. If you do want to have chunks which are way bigger than this, remember, you can 100% query all of the debris and everything that chaos creates for you, right? So if you had large chunks of debris raining down into your playable area, and you want to put some work into your AI actually dealing with it, they could shoot it if they want to create a path. They might be able to climb on top of it or mantle over it. They could actually use it as dynamic nav mesh. So if you want to create that next generation cover shooter that's coming out, where you rain down huge chunks of debris, you're destroying buildings, and all of that ends up as dynamic cover in your playable area, and both the player and the AI can use it, this is possible with chaos. So once we're past navigation, we of course want to start using want to use destruction as a tool. And you know what's coming, right? The first thing we want to see is how we can kill people with it. So I apologize for the low quality of the videos. Once again, I'm a game designer, and this is literally video from the first time we hooked all of this stuff up in one of our test levels. But here we see just a simple geometry collection raining from the sky and killing somebody underneath. So if you want to create depth of destruction, Chaos gives you all the information about that debris and its mass that you need. So every one of these break events is going to tell you how big the chunks were that actually hit you. It's going to tell you where it came from and what the velocity was. So if it's big enough, you're going to trigger death, like right here. But if you want to make it smaller, you might play a flinch or some sort of hit react. If you want to have something that hits next to an AI, we can send that event from chaos to the AI system, and they can play the appropriate result. And again, because you get positional information, if it was coming down from the sky, you can react to that as well. Just some examples, but this is how we already did all of the heavy plumbing, is pretty much what I want to say here, where we made sure that the communication between chaos and those gameplay systems is all there for you. Now, this is AI acting autonomously. And this was really important to us so they could react to it, because as soon as AI actually starts reacting to all of those break events and all of this chaos that's being caused in the world, that adds a whole nother layer, right? Because if AI is aware of what's happening in the world, then the actual destruction becomes more powerful as well. So these are autonomous systems that you create, but sometimes as a designer, you want to be able to detect all of this stuff as well. So I want to give you one example of how we did it for this specific demo. We created this little class blueprint, which we call a destruction detector. And we can put this at any part of the demo, around this pillar, for example, which is a geometry collection. And then we can listen to how much damage has been dealt inside its volume to that specific geometry collection. And then this is just unreeled, right? So you can just listen to another event, and you can act on that. So in this case, I'm listening to when this pillar has been destroyed. We're marking pillar 11 as destroyed. And as you're playing this demo at the booth, you're actually going to see progression gated a lot this way, where chaos is hiding behind one of these pillars. We ask you to destroy the pillar, and then we're moving on. That's what's actually going on under the hood here. Now, instead of detecting damage, we actually could also have detected the amount of mass, the amount of debris that we generated. Ended up not using this as much in the demo because I found that using damage was actually an easier way to actually do the progression. But you could totally do this. You could use the same kind of destruction detector, and you can listen to, in this volume, how much rubble has actually been created. And then you would go into Blueprint. This is a sample blueprint where you can just look at your chaos break event. And you can see it's going to give you a whole bunch of information, but the important part is it's going to tell you how much mass has actually been generated in this volume by destruction. So if you want to put a container somewhere on the street and you want to detect if somebody has rained down enough debris into that container, and then you want to advance progression when that container is full, you would put one of these destruction detectors into that container. It's going to tell you when it's full. Right? It can just accumulate the amount of mass. And once again, you can trigger an event based on that. Now, if we bring this together with the earlier nav example, this is also how we invalidated cover. So we have these cover points. They're all around the world. They're incredibly standard. But we created the simple mechanisms where we actually hooked up to these destruction detectors. There are ways in which you could generalize this even more so. But in our case, we were just listening to the destruction detector. It told us when a pillar had been destroyed. It invalidates cover. And this is how AI is actually making decisions to now not take cover behind this pillar anymore, because it's been shot to pieces. These are some simple examples, but hopefully they give you a good idea of how, as a designer or a gameplay programmer, you're going to interact with the system. We're just scratching the surface here. I could talk about this for hours, and I hope we actually continue this discussion at some point if you stop by at the booth. But hopefully this gives you a good idea of what we're actually doing to design with chaos. Now, before I hand it off, I want to bring up one more topic that might be on some people's minds, which is, so does all this work with networking? And we don't really want to go too deeply into it, but I'm going to tell you, this is going to be Epic's physics system of the future. We've been thinking about networking from the ground up because you know about the kind of games that we're making. So be assured, if you're thinking about this as a physics system, you should start thinking about network games, and they will be supported by Chaos. So that's pretty much it for me. Please stop by the booth. Play the game. We're going to be hanging out to answer your questions. I'm very excited to talk about more ways in which you can actually enable incredibly expressive gameplay based on this. Please don't go to the booth right now, because we have Jim Van Allen come up, and he's going to tell you how we made all of this look as awesome as it actually does. Thank you.
Everybody. So I'm really excited to be here today and talk to you about the art side of making this demo. We had a super talented team on this project, and I can tell you I had a great time playing with it every day for the last few months. This is pretty much what you would see on my workstation for the last, I don't know, month or so. I'd load the level and start playing and to test one thing or another, and then 10 minutes later I realized that I completely forgot what I was doing and I was just shooting everything. So I was putting this presentation together and I started to ask myself, as an artist, what do I really want from a destruction system? And here's what I want. I want to take any random geometry, I want to fracture it into a random pattern, allow a random user to hit it with random forces from any random location, and control exactly how it looks. So boiling everything down, I found everything revolves around this one keyword. This is what I really want. I want something that looks like total chaos to you, but actually behaves exactly the way I want it to, runs in real time, and then maybe meets the needs of the design and environment art and engineering and all those guys. So for me, everything in this entire system revolves around this. And that starts here with a new type of asset we're calling geometry collections. Now, geometry collections are built specifically for destruction in Unreal. Mike's going to go into the details about how they work and what they really do. But there's a couple of key points for artists. So they can be built from one or more static meshes, including those gathered in blueprints or even nested blueprints. So you can see on the left here you have, I don't know, hundreds of meshes. You click the button and then you have one single geometry collection that you work with. They let you choose what you're simulating and what you can just ignore. And they give you a lot of flexibility in terms of how you organize and author destruction. So in the first section of the demo, we showed almost every static mesh is its own geometry collection because that was just the easiest way to manage that. In the middle section, it was more module. And then in the final bit, because we're dealing with entire buildings, we broke them up to like 12 geometry collections for that one. And the thing that's really cool is it just gives you the power to decide how you want to manage these things. So we have our geometry collection. Next thing we do is break it into pieces. One of my favorite things about this system is, aside from a few things that were hand-modeled into larger chunks, every single thing that we fractured in this demo was done in Unreal. We can fracture each part individually. We can apply patterns across multiple pieces. We've got your standard Voronoi fracture, but we've also got a pretty nice suite of tools that let you dial in a specific look. We've got your radial fracture, some clustered Voronoi. My favorite is planar fracture, which lets you get a nice organic look. It's really up to you and the needs of your system for how you want things to look. So in a budget-conscious world, subfracturing lets you control where you want to add details. So you can select in the mesh, and we fractured this one into 10 pieces. Then you can select a part of it and subfracture and keep going down and down. Now, what's cool about this is the chaos system keeps track of each subsequent level and stores that information into something that you can control, a cluster. And here's an example of a mesh where each fracture level is combined into its own set of clusters. And this is different from a lot of other systems where those things are all glued together and then processed as all the separate pieces together. In our system, we treat each node as a single object. And until enough strain is applied, it still treats it as that one thing. And so as you can see here, we're simulating level 1. It's only calculating those pieces. Conversely, if we turn clustering completely off, you can see every leaf node falls, which is not super fast, but also doesn't really look good. And then by tweaking the values, you can get a result that looks good and performs well. And so this video shows that in action. It was tweaked a little more carefully by the artist. So if you're like me, and you're too disorganized, or what I call artistic, to meticulously keep track of every fracture and the levels and all this stuff, we have an awesome tool that allows you to flatten it all down into one thing and then procedurally set up your clusters. This allows you to effectively spam fracture an entire building and then sort it out after the fact. So you can reduce complex fractures like I don't even know how many are here, but you can take a building and fraction it into 5,000 pieces, and then work your way up level-wise to 2,000, 1,500, all the way up to 5 or 10 pieces. And this lets you explicitly control the density of each level and allows you to control the performance. And what's really cool about this is because we can control these things, it's one of these really fun times when the needs of performance and the needs of art work together, because you really don't want, it looks bad if you have too many small pieces floating around. It looks bad if you have too many big pieces floating around. Okay, the next thing I need to talk about is the connection graph. This is a lightweight connectivity map. It's a bit of a different paradigm for destruction simulation. So here you can see we have some statically anchored pieces at the bottom and top, but everything else in this scene is hanging out waiting to be dynamic. Rather than swapping from a kinematic to dynamic state like a lot of other systems, our system applies strain, which in turn breaks the connections and causes chaos to ensue. We found this to be a great way to maximize interactivity while still retaining control over the amount of rigid bodies that are activated. And it also can detect when something is just hanging out by itself and things will fall. It's pretty cool. Okay, so we have everything set up. We're ready to play with it. How do we interact with it? The answer to that is fields. Fields are the way that artists can directly interact with and control simulations. The fields can be used to control any attribute on any part of your geometry collection. You want to vary your mass, you want to make something static or dynamic, you want to make a corner more breakable or less breakable, pretty much whatever you want to do, apply some force, fields are the answer. Now, fields are created and controlled through blueprints. In this example here, we're applying some strain followed by some linear force. We have radial fall-off fields, which is basically a spherical volume, controlling where those are applied. Because this is a modular system, the really cool thing is you can stack all these things together. You can add noise multipliers, pretty much anything you can imagine. This example here is the basis for a weapon, just a generic weapon. But for example, you could put a delay in there, then you have sticky bombs like we used in the demo. You can multiply it by 1,000, and then you've got a high velocity cannon that we also used at the end. Okay, so now I'm going to show you 3 types of fields that we used in this demo. This is anchor fields. They pretty much do what you would think. They lock any nodes within the volume into place. They're kind of boring, but they are the building block that we use to set everything up. So in this level here, we're using anchor fields to lock the top and bottom of the pillars and the walls, and that way we can control exactly how much they collapse and just where they go. This is my favorite one. This is strain fields. They apply strain to the geometry collection, and as we said before, enough strain and you break the connections and things start happening. One of the really cool features of this system is that the strain required to break each cluster is tuned by the artist. This allows you to specifically tune your simulation for aesthetic quality, gameplay interactivity, or performance as needed. In this example, the scary face guy is the strain field, and he's being animated upwards and applying force as he goes. The box underneath it was added by an artist, and that's a culling field that keeps forces from being applied there so that you don't have things just go completely crazy. So it's just one example. I'm really looking forward to seeing what people come up with when they get their hands on this. And finally, the sleep field is a pretty straightforward concept. Again, they put things to sleep. But it's a really powerful tool. Here's another video to show you what's going on. So any object that moves below a predetermined velocity is put to sleep. The cool thing about these things is they can be woken up if you shoot them or if a big piece falls on them. So they're not actually removed from the simulation, but you don't pay the cost of calculating them while they're sleeping. Now, aesthetically, as an artist, this is really great because it keeps things from rolling around and just getting wonky and crazy. And then finally, it acts like a direct performance throttle for a whole level. So if things are going a little slow, not quite hitting your performance margins. You can raise your sleep fields. You can increase the thresholds. It basically gives you a one-step place where you can get the performance you need. A fun thing to do is turn it off and watch everybody start freaking out, and then you turn it back on. Like, hey, I saved the day. It's great. But, I only did that a couple times. I didn't do it that much. They got mad. But, no, I'm just kidding. So as you can see here, I can shoot this all day. I didn't, but I could. And you won't see any drop in performance. You can completely demolish this level. It's a really awesome tool. And then the last thing I'm going to talk about is large-scale simulation caching. And with the caching, high-fidelity simulations can be pre-cached and played back in real time. Now, the result is not a movie or a static thing. It's a kinematic geometry collection. And that means that you can author large-scale destruction events and still allow interactivity with the player and the environment. And so that's it for me. I hope this gives you an idea of how artists can control this system, and I can't wait to see what you guys do in the future doing destruction in Unreal. So here is Michael Lentine, our lead physics programmer, to talk about the technical aspect of the system. Thanks.
Thank you, Jim. So my name is Michael Lentine. I run the physics team here at Epic Games, and I'm going to talk a little bit about the tech behind the demo we just showed earlier. So when you start out to build a physics system and a destruction system, we tried to figure out what are the primary things we're trying to accomplish here. So the number one goal we always had in mind was essentially to give the power to our content creators. And this means we had to create a number of new features for both the physics and the destruction aspects of the system. We also wanted to make sure that the system can scale. And that means two different things. So on the one hand, we want the system to be able to scale from low-end devices to high-end devices. But we also want the system to be able to scale to hundreds of thousands of simulatable objects, which we haven't had the capability to do up to this point. So the first thing we had to come up with a way of dealing with was non-convex collisions. So typically, we are limited to fairly simple collision objects. And this becomes unwieldy when we have, say, 100,000 objects that somebody has to author, as they typically have to go through and author most of those things by hand in order to get the type of look that they want. However, what we decided to do was come up with basically a completely different system that has these three goals in mind. So it has to be art-directed. So when you're fracturing something like this building, you can create the pieces that exactly you want, alluding to kind of what Jim was talking about earlier with it basically has to work with random geometry and random fracture patterns. It has to be accurate, because if it's not accurate, then you're going to get all sorts of popping effects when the buildings start to break. And it has to be fast. So we don't want to necessarily pay the cost of traditional methods using full meshes in order to collide with and things like that. So we came up with a completely different collision representation that can address these three different issues, leading to the type of behavior you see in this video here. The other thing, which you've heard a little bit about so far, is the field system. So we use this pretty heavily in the demo that we showed. The fields are really a more generalized concept than what we've used them for so far. All they effectively are is a region in space, so it can be a sphere or a box or pretty much any piece of geometry that you can think of, and it affects some parameter kind of within that region. So we use this in our demo for affecting strain values within our destruction simulations, for affecting forces, but it can also be used to affect other things. So suppose you wanted a specific region of this floor to have a different friction value than a different region of this floor. You could simply set a field on that region to specify kind of what that friction value would be. So this is a simpler example than the one Jim showed, just to go through one of the simplest thing that we actually had in the demo. So this is one of our force application fields. So this is very simple. We have a radial fall-off field. So we just start at a center with a radius, and we decrease the magnitude from the center as we go out to the edge of that radius. We then have basically a random vector field, and that random vector field basically just adds noise to our force applications. We can simply combine those two fields to create one of the force effects we have every time you fire a weapon in our chaos video. A hugely important aspect of the system is to be able to integrate with other aspects of Unreal. So the most important one for things like destruction is the ability to integrate with our Niagara particle effects. So we do this by capturing a number of different events within the chaos physics system. The two most important are collision events. So every time an object hits another object, you'll get essentially an event of when that happens, as well as various properties like location and mass and things like that. We also record breaking events. So every time a piece or a chunk breaks out from, say, a building, you'll get an event that signifies when that happened, as well as the properties associated with that. Now, this makes it really easy to simulate things like dust and smoke, which you expect from the ability to destroy large buildings. But it can also be used from various other subsystems. So the two other subsystems that we used heavily within this demo were gameplay, which Matthias talked about a little bit earlier. So that takes these events and uses them to create character reactions or to kill characters, and for audio. So every time you get one of these events, that sends an event to our audio system, which then can play various effects depending on the properties of that event. One problem that we do have with passing forth data is when you're dealing with 100,000 objects or something of that scale, the amount of data that you're passing is astronomically large. And so that can get slow pretty fast. So what we did to avoid that is we have a number of different filters that can be applied for these different systems. So for instance, when we're transferring events into Niagara, we use a spatial filter so that if you have like 10 different collision events in the small left corner of your building, that can basically be registered as a single event. Similarly, for audio, we can essentially sort our events based on mass and then play audio events for the biggest objects. So we don't just hear constant noise from everything colliding with everything, but we hear kind of all the big important events that we get in the simulations. We talked about this a little bit. So interactive caching is something that we wanted to be able to achieve with this system as well. So this achieves the goal of trying to be able to scale from low-end devices to high-end devices while making everything interactive. So obviously, you just don't have the amount of computational power to run huge simulations when you're on a low-end device. So instead, what you can do is pre-record simulations inside of the Unreal Engine and play them back. And at any point, any of those objects can start being interacted with. So the way that works is when we start our simulations, we effectively put all of our objects into a sort of sleeping state. And then when those objects start interacting with other objects or interacting with the player, they start becoming active. This allows us to simulate, in some sense, hundreds of thousand objects while only needing to pay the computation for simulating a relatively small fraction of them. And the fundamental goal for this is to give us dynamic interactive worlds in any environment and in any setup. Another important aspect of the system is because it's entirely authored inside of the Unreal Engine, the amount of iteration time in authoring these assets is very small because you're not constantly going in and out of third-party packages. So one departure, which is not something that's necessarily showed off too much, is sort of the way that we do multi-threading of physics inside the engine. So right now, the engine has two primary threads, our render thread and our game thread. Our game thread is largely responsible for our physics simulation, but this limits the amount of gameplay events that you can do in conjunction with physics. So what we've added the ability to do, which is not a requirement, is to have an additional physics thread. So this gives us a number of interesting capabilities. One, it easily scales when you have 3 different threads that you can utilize. It also gives us the ability to tick physics at an entirely different rate than you would tick the rest of your engine. So if you want to tick at a fixed time step, that is completely possible within the new system. If you want to tick at, say, 120 hertz because you want your physics to be super accurate and you don't have a lot of it going in the scene, that's completely possible. If you want to tick your gameplay at 60 hertz and your physics at 30 hertz, that's also completely possible. So we talked a little bit thus far about geometry collections. So geometry collections are a new type in the engine that sort of live between what a skeletal mesh is and what a static mesh is. So static meshes are really simple objects that are great for things that basically aren't changing or moving at all, which means they're very difficult to use for destructible assets unless you use a skeletal mesh per part of your destruction, but that gets really expensive really fast. So the alternative that existed currently in the Unreal Engine is skeletal meshes, which pay a fairly large amount of cost to process because they're really meant for things like character scanning and stuff like that. So what we did was create a lightweight, scalable system that can have hundreds of thousands of these bone-like elements in them and can simplify the computation. So in this particular asset, this can be viewed as a single geometry collection. And you're essentially only paying, say, draw or you're only paying the draw cost basically for the number of materials that you're making in this building, and yet we can still blow it up and have all the pieces move independently. So as part of the system, we wanted to make sure that the iteration time was small, and we wanted to incorporate a number of cutting tools directly inside of the Unreal Engine. So when these tools were released, you'll be able to take any static mesh that exists inside the engine and just start fracturing it and playing with it. And we talked a little bit earlier, so I'm not going to go into too much detail about the different types of ways that we can currently fracture stuff, which include things like Voronoi fracture, plane cutting, and image-based fracture. Another important of the system, which was related to the goal of scalability, was destructible LODs. So destructible LODs are a bit of a new concept and aren't quite the same as something like geometric LODs, which is obviously just when something goes farther away, you change your rendering representation. So this is related to sort of the level hierarchy that Jim was talking about earlier. So when you take a fractured mesh, you can break it up into a small number of pieces, say 6 pieces. You can then take each of those 6 pieces and break those each into 10, and each of those 10 into 10 more, and so on and so forth. So this gives you 2 capabilities. So one, it gives you the ability to do a lot of secondary breaking, which is very satisfying. So here you can see in these examples, we have these big chunk of pillars that kind of fall off as we shoot the tops and the bottoms out, and then you can continue to destroy those pillars after they fall off. It also gives us the ability to make it easier to scale with a single artistically created setup. So if you wanted to have a low-end device and a high-end device, and you have this set up with 6 to 60 to 600, or whatever your breakdown happens to be, you can take your low-end device and say, well, I never want to simulate more than those 6 objects for this asset, and basically lock your LOD at that point. But you can allow higher-powered devices to break those pieces up further and simulate 600 objects. And that means that you can have a single artistically created setup, so you don't need to create, say, your destruction for this device, and your destruction for this device, and your destruction for this device, and give you kind of the scalability between low-end and high-end platforms. So finally, we had to come up with a method of doing dynamic strain evaluation. And this is important because as we get to these large scales in terms of number of bodies, it becomes fairly daunting to try to completely author these things manually. So what we do is we build a connection graph, which you saw in Jim's slide, and then each of those connections in that graph essentially has an allowed strain. That allowed strain can be set through fields, it can be set through parameters on the object itself, or a number of other ways inside the engine. We then evaluate essentially what that strain is when anything interacts with that geometry collection. And so if that interaction results in a strain on that connection being bigger than the internal threshold, we break that connection. So this gives the automatic ability to kind of break things up. It also gives interesting effects. So if you do things like have a building that's a geometry collection and blow out, say, the entire center of that building, then the entire top will start falling because that connection graph is now disconnected from the ground and has nothing effectively holding it up anymore. So to give you a sense of kind of what the system is kind of capable of, I'm going to show a little video of a modified version of the demo that we just showed. So as you can see through this, even though we had a very specific goal in mind when we wanted to create this demo, we can effectively handle a fairly large scale of objects that are simulated in real time and can be effectively authored with the rest of the system. So I'd now like to hand it over to my colleague Jeff from Intel, who will talk a little bit about how we're making chaos faster.
Thanks, Michael. So I'm Jeff Roos. I'm a senior developer relations engineer at Intel, and we work with Epic quite closely on this demo to make it even faster. So we worked with Epic to optimize the low-level solvers, the data structures, and thread parallelism, and we helped them get the most out of their CPUs that they possibly could, because this is running on a pretty high-end machine. So what did we do? Well, and what did we learn? So our key learnings is that C++, despite being a low-level language, is really bad at SIMD. We integrated a technology from Intel called ISPC. What that is it lets you go wide, and I'll talk about that in a minute. And we saw 3x gains in many critical areas. The second thing is that tset, if you're familiar with the Unreal containers, can be really bad in high-performance situations. So when you're breaking up and finding intersections between objects, you need to grab those into an array, sort them, and remove, rather than guarding duplications with something like a tset, because we were spending all of our time doing hashing, which isn't exactly what you want to do. You want to have more stuff on the screen. Also, another key learning was parallel 4 can be overused. It's really, really great at hiding bad cache code. And some oversubscription is good, but you don't want to go overboard with many thousands of jobs. Batching is super helpful if your data access patterns are cache-friendly, but also test to make sure that if you're using parallel 4, that just running it on a single thread is not faster, because in a lot of cases it can be. So CPUs since the early 2000s have had vector units that programmers can use to speed up their code. That's what's known as single instruction multiple data. It gives you the ability to do 8 floating point adds in one instruction, for example. One of the problems with C++ is it's hard to get the compiler to vectorize anything. Differences between compilers means differences in performance. The usual solution is to use compiler intrinsics that you have to update with new instruction sets, and that enter the ISPC compiler. So the ISPC compiler is the Intel Single Program Multiple Data Program compiler. We have great names at Intel. So what does ISPC give you? It gives you implicit parallelism in a language that looks like a shader language, but it runs on the CPU, which is critical for something like chaos. Like a shader language, it assumes SIMD by default. ISPC also acts a lot like GPU shaders in the way that they're executing, with some important differences that I'll talk about in a minute. A big benefit is that programmers can write ISPC once and compile to many vectorized instruction sets such as SSE4, AVX, AVX2, also Neon, and it supports PS4 and Xbox, so this will run anywhere. If you're compiling for multiple instruction sets, it also auto-detects the highest instruction set that your computer uses, so that it uses the fastest one for your CPU. So you don't have to update your intrinsics anymore, you just recompile. So we use this a lot in the new physics engine, and it will be available for all programmers in Unreal projects soon. The basic workflow there is you include a module in your build CS, you add ISPC files to your project, you include the generated header file that links ISPC and C++, and then the Unreal build tool handles the rest, including packaging your object file into your project. And all of this was done to make it really easy for all of you to use it. So what is ISPC good for besides chaos? It's really good for dense compute-bound workloads, heavy math like chaos did, finding physics intersections, cloth or CPU vertex transformation. It's best when you use it with contiguous memory, manipulate load stores, like if you're using a T-array, for example. It works best when there's no data dependencies between operations, and it's especially useful when combined with parallel 4 and some kind of batching, and making sure that your cache is, your algorithm is cache-friendly. Remember how I said ISPC acted a lot like GPU shaders? They do, with some important differences. Whereas shaders all run independently, each SIMD and ISPC runs one instance of the program. The difference lies in that ISPC runs all of the SIMD lanes in lockstep and always guaranteed to converge at the end. GPU shaders will finish execution at different times. So when you have branches in your code, those not taking the branch are turned off and then back on when the branch scope ends, and that's, then all will continue. That's actually faster than it sounds. One neat thing about this convergence is the ability to do reductions across SIMD lanes. For example, if you're trying to find the sum of an array of integers or the min or max, that's really fast. We use that quite a lot to make chaos even faster. And the bottom picture here shows what ISPC code looks like and what it generates. We have an RGB to gray that converts n values and stores in 3 multiplies and 2 adds. With AVX, you're running 8 of those at a time. 2 of the multiply adds can be fused into FMA instructions, and this is roughly 8 times faster than a scalar implementation. So you can see on the bottom there what ISPC code will turn into. So that's about it, about what Intel did to help optimize the chaos demo. Look for the changes and the ability to use ISPC in an upcoming release in UE4, and also check out the booth, Epic's booth, for this really cool demo. Big thanks to my co-presenters from Epic, who I'll invite back to the stage, and thanks for coming to this talk.
And thanks to everybody. Thanks to everybody at Intel who helped us optimize this. I think the results really speak for themselves. I mean, this looks amazing. So this is the end of our talk. Unfortunately, we do not have enough time for an actual Q&A session. So we do hope that you stop by the booth. We have 2 of these stations set up. You can drink beer, you can eat popcorn, you can smash some stuff. But just as importantly, we have a whole bunch of these workstations set up. So find one of the developers. If you have more questions or comments, come and find us, and we'll be really happy to talk to you. Have a great GDC. Thank you.